Now we're gonna look at how to sketch a shear force diagram. Okay, so on this beam that we already calculated the reactions, this beam over here, we already calculated the reactions. So we're gonna use that same beam to learn how to sketch a shear force diagram. Guys, so I just put down the reactions because we already calculated it. So if we look at the notes here, the notes explain how to sketch a shear force diagram. First of all, the shear force diagram is the same size as the loaded diagram or the loading diagram, the beam with forces. It's a closed diagram. It starts at 0 and it finishes at 0. How do you sketch a point load? You always start from the left hand of the beam and you go towards the right end. A point load is sketched by sketching a vertical straight line. If it's a downward force, we take it as a negative, we sketch it downwards. If it's an upward force, we take it as a positive, we sketch it upwards. In between the forces, where there is nothing, where there is no force, we sketch a horizontal line. Then a uniformly distributed load, we always take it as a negative because it's seated on top of the beam and it's exerting a downward force. So we always sketch it downwards. Now, for a uniformly distributed load, we make a sloping line. For a point load, we make a vertical straight line. For a UDL, we make a sloping line from where it begins to where it ends. Okay. So let's look at the example to see how we can apply what we have just discussed. So first and foremost, get your beam, which is the same size as this loaded beam here. So this beam is 3, 5, 8, 10 meters. It's 10 meters long, okay? So let me sketch that. So the one that is given on the question paper is not necessarily according to scale. Okay, let me use this one, otherwise that one is too big. I don't want to make it too small, so I'm gonna make it 10 meters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So I've just scaled it and show each meter, because when you show each meter, then it's easier to work with. And then I also want to have my references for A, B, C, D, and E. So those are all the points where you have a force. So this is A, and B is 3 meters after A, and C is 2 meters after B, and then 3 meters we have E, and then we have the end. So you're always gonna have a reference by the beginning as well as by the end. Okay. Then our beam will always start at 0, the shear force diagram. You can label it here, shear force, because the forces were in kilonewtons. You can say kilonewtons. If you label it over there, then you don't have to label each point. But if you don't put this label, then you must label each point and show that each point is in kilonewtons. Okay. So now we're gonna start. So immediately at this point, we have a UDL of 5 kilonewtons and it's covering 3 meters. So we start from 0. So we will say 0. Because it's a UDL, we subtract. UDL is always negative. It's facing down. UDL of 5 times 3. And then it takes us to minus 15. So we come down here to minus 15. Okay. And then we are now at B. We are at minus 15, then we get to B. So this is A, this is B, C, D, E. All right. And we're already at -15, so the net force is B and it's upward. So if it's upward, we take it as a positive, we add 39.071. It takes us to 24.071. So we go up to 24.071. Okay. And then at this point, at point B, we have a UDL of 5 covering 2 meters. So we subtract it because it's a UDL of 5 covering 2 meters. It gives us 14.071. So we come down to 14.071. At this point, this is point C, we have a point load of 10 and it's facing downwards, so we subtract it. It puts that at 4.071. So we come down to 4.071. From C to D, we have no force, so we go horizontally across. Then at D, we have a force of 10 and it's facing down, so we minus 10. It takes us to a negative 5.929. Come down to a negative 5.929. And then at point E, we have, E is actually here, to 1.929, not here. Okay, so at point E, we've already done the point load. Then we have a UDL of 8 covering 2 meters. So we subtract the UDL of 8 covering 2 meters. It gives us minus 21.929. Because it's a UDL, we make a sloping line. Minus 21.929. Then at minus 21.921, we have an upward force that is 21.929. So that takes us to 0. It's a point load, so we go vertically straight. So it takes us to 0. You don't necessarily have to measure these values, 15, 24, all that, but your proportions must be correct, okay? Like a 21 is a bit lower compared to 15, a 24 is higher than 14. So just look at your proportions, okay? So let's do the second one also as an example. Okay. Let's do it as an example. So let's quickly just calculate the reactions as well for this one, because we haven't got the reactions now for this one. Let's quickly apply our method to calculate the reactions. So we said to calculate the reactions, we first change the point load and we first change the UDL and we make it a point load. So this one will be a point load of 10 times 4, which is 40 kilonewtons. Just to calculate the reactions, we change it to a point load. And then we can take moments. So let's take moments by B to calculate C, okay? So sum of our clockwise moments will be equal to sum of the anti-clockwise moments. And then clockwise, we're gonna have 40. How far is 40 from B is 2. Then the next one we have is 8. How far is 8 from B is 5. Then the next one we have is 5. How far is 5 from B? It's 6. That's all for clockwise. Anti-clockwise, we have C. How far is C from B? It's 4. Then the next one we have anti-clockwise is 5. How far is 5 from B? It's 1. Okay? So we're going to get the reaction at C. So here we have 40 times 2 plus 8 times 5 plus 5 times 6 minus 5 times 1. It gives us that, divide by 4. So it gives us 36.25. So that's the reaction at C, 36.25 kilonewtons. Okay? 36.25. Let me put it there, 36.25. And then when we have C, to get B, we can take moments at C, or you could even use Newton's third law, now that you have one upward force and all the downward forces. Okay, so let's do that actually. B will then be all the downward forces minus that upward force. It's gonna be 5 plus 40 plus 8 plus 5 minus 36.25. It gives us 21.75. 21.75. So B is 21.75. Now that we have our reactions, we can sketch the shearing force diagram. Okay. So this is 4, 5, 6, 7, 7 meters long. So just to have it big enough, I've just doubled up the scale. So my advice is always measure your beam and show your meter intervals. Show your meter intervals as I'm doing here. 1, 2, 3, 4, 5, 6, 7. So that beam is 7 meters long. Then you have a reference at each point. So that is A. B is 1 meter from that. Then 4 meters from that. 1, 2, 3, 4. It's C. And then a meter from there is D. And then we have E. Okay. So we can label it A, B, C, D, E. And then again, we label it shear force in kilonewtons. Put that label over there, shear force in kilonewtons. It's always gonna start from 0. Okay. So we are now at A. So what do we have at A? We're gonna say 0 minus 5 because it's a downward 5, so it's gonna be negative. So it takes us down here to minus 5. So we come down here to minus 5. I think I should have used the red. It comes down here to minus 5. And then at minus 5, from A to B, there's nothing. So we go across. We go across. And then at B, there's an upward force. We plus the upward force of 21.75. It gives us 16.75, a positive. So we go up 16.75. Then that force we don't consider now as we are doing the shearing force diagram. That one, it was just to calculate the reactions. We are now at 16.75 FB, and the next force is the UDL. We subtract the UDL of 10 covering 4 meters. So it puts us at minus 23. So we come down here to minus 23. Minus 23 is quite down. So this is minus 23.25. At minus 23, we are now at B. So the next force is 36.25 and it's upward. So plus 36.25. It gives us a positive 13. So we go up to a positive 13. That is a positive 13. At C. So at C, between C and D, there's no force. We go across. Then the next force is 8. We minus the 8 because it's facing down. It brings us down to 5. So 5 is here. Between D and E, there's no force. We go across. Then at E, we have a -5. It takes us to 0. So we come down to 0. Yeah. So that is how it would have looked like. All right, thank you.